Yes, hello everybody. Welcome to this week's lecture on DECA 2. So for the last 2 weeks we have been talking quite extensively about static analysis, and I've also shown you a couple of actual applications such as FlowDroid. And now this week I want to talk about some of the limitations of static analysis and how one can also boost static analysis by incorporating some dynamic information as well. And I think that's a really interesting line of research that has come up every now and then in the last 10 years or so. And I think it's a bit of a trending topic, and there are definitely some clear benefits in some cases. And I want to discuss these with you this week. And in particular, I want to talk about what I frequently call hybrid analysis, or other people have also called it blended analysis. So this is basically an analysis that combines static information and dynamic information into one single analysis run. And this has been implemented in a number of different tools. But here I will talk about two different approaches that we have actually developed in my own lab. One is called Harvester and the other one is called Heapster. And I will first talk about Harvester and how it can be used to actually extract runtime values out of running applications, and why that is useful and how static analysis supports this. And then second, I will show you a large-scale app analysis, so Android app analysis that we actually did with Harvester, with some interesting, or one could even say disturbing findings. And last but not least, I will also talk about augmenting static analysis with heap information, which is a much more general approach that can basically be applied to pretty much any static analysis. And it can also be useful in selecting the right trade-offs for your analysis context. So let me start by talking about Harvester. So I should say this is not just work of my own, this is really work of some very bright PhD students I've had the pleasure to work with. So Siegfried Rasthofer and Stephen Arts. Then it was actually also largely a student project by Mark Miltenberger, who really very extensively worked on this with a lot of courage, and so he really made a great project out of this. And this was published at NDSS, which is one of the top security conferences in 2016. So the motivation that we had back then was that we wanted to be able to better analyze Android apps, and in particular we wanted to have a pretty good approach of identifying malicious malware apps. So malicious apps are still a problem in current app stores, but they were an even larger problem back then because this technology did not yet exist. And I already showed you when I talked about reflection that there are some apps that do things such as this, right? So there is, for instance, a pretty old malware, Fake Player, from 2010 that used to look just like this. So this was relatively simple. It was just trying to send out premium rate SMS messages by getting an SMS messenger and sending a text message. Obviously that's a code pattern that is fairly easy to identify, also using static analysis. And that was the state of the malware art back in 2010. But then if you look a few years later, we had malware that rather looked like this, that used reflection and dynamic loading and so on to actually obfuscate what it was doing. And essentially this is actually the same code, right? So this is doing the same, or executing the same functionality that we saw on the previous slide. It's just heavily obfuscated, and you can imagine a static analysis doesn't really have any chance of finding out a lot here, right? I mean, we do see some class for name calls, but you see all the names have been mangled, so they basically use some symmetric encryption here, sometimes even using AES these days, to actually statically encrypt and then dynamically decrypt these different identifiers, so that really a static analysis has yeah, I would say really no chance of extracting these values without doing anything dynamic, without actually executing the code. And so in this harvester paper, we had basically 3 contributions. So we first sought to build a fully automatic extraction of runtime data. So our goal was to extract these values that you just saw. So for instance, these strings that are passed to the reflection API dynamically, because the hope was that once we have these strings, that tells us something about what the app is executing and whether or not it might actually be malicious code that executes there. As a part of this, we also wanted to have a fully automatic resolving of reflective method calls. So that goes into the direction of Tamiflex, but it will here go a little bit beyond this. I will still be talking about this. And a third point that I won't talk too much about this in this talk here is improving the coverage of existing off-the-shelf static and dynamic analysis tools. I mean, you can imagine this. Once we are able to fully automatically resolve reflective method calls, then we can incorporate their effects back into the program. So that's basically what I already explained in Tamiflex's booster component. And then your static analyzer can gain substantially in recall when it analyzes the boosted program. And I've explained that for Tamiflex already. And this harvester approach essentially has an equivalent component itself that we also evaluated in the paper. So if you want to find out more about this component, I encourage you to take a look at the NDSS paper and you will find the details in there. So the basic idea behind harvesters is as follows. So you take an Android app such as this one. I think that was Angry Birds back then. And then this app actually has some API calls that are of interest to us, right? So let's assume we are a malware specialist, a malware analyst, or maybe we are even an application that tries to automatically triage malware. Then we might be aware that these are interesting API calls to watch out for, right? So if somebody is sending a text message that might be dubious, right? Or somebody is loading classes using class for name, we might be interested in knowing what is actually loaded there. And so the input to Harvester is exactly a set of such signatures, right? So we tell Harvester, first of all, that these are method calls that we are interested in, and that these in particular are arguments that we are interested in, right? So we basically have a file format that allows us to have a customized specification of these API signatures and their parameters. Then this is given both to Harvester, right? So the app under analysis and this configuration or specification. And then the idea is that Harvester will do its magic and it will output exactly this for us, right? So it will tell us, for instance, for this app, we have monitored dynamically that there were 2 calls to send text message, and one with this parameterization and the other one with this parameterization. And by the way, we also saw a call to class for name where the program tried to load the class SMS manager. And this can then be fed into some other analytics engine, right? So for instance, there are now a number of companies that try to keep their app store clean, also using machine learning. So they will use lots of features of the apps that are being analyzed to determine whether or not it is likely that a certain app is actually malicious. And you can imagine that these can be very useful features, right? So if you see certain numbers popping up here and you see certain classes being loaded, that can be a pretty good indicator, at least compared to other purely static features, on whether or not this app is actually malware. Now the problem is, like I said, the applications, they're heavily obfuscated, right? And that can cause a little bit of trouble, but I want to show you here how Harvester is actually dealing with this. So Let us assume that this is a control flow graph of some app's code, okay? And now we have marked these two parameters here as interesting. So these are parameters that Harvester should please extract for us, okay? Then we could first think about just doing a pure static analysis here, right? But yeah, that static analysis could basically walk back here through the control flow graph, and it could sort of try to compute the data dependencies that we see here, right? So number, it's being defined up here, message, it's being defined up there. And we can try to extract these values, but the problem is we won't get very far, right? So at the latest, when we see this message here, in this case, I've actually AES decrypted it. So the static analysis won't really be able to make any sense of it unless it has some special handling of these decryption routines. And there can be an arbitrary number of these routines. So you probably don't all want to model this statically, right? So that's probably not the way to go. For the number here, it might still be doable, right? That's a simple string concatenation, and many static analyzers model this already. But at the latest up here, it's not really what you want to do. So you can think about using dynamic analysis, and here I'm talking about a purely dynamic analysis, okay? But then you will see that many of the actual malware apps, they have basically recognition components that try to recognize whether or not you are actually running the app in an emulated environment. And there are certain runtime clues that an app can obtain in order to figure this out. So for instance, there might be the case that this build fingerprint here, it actually starts with generic, and that's typically the case when you're running the app not on an actual phone, but in an emulator. Similarly, there might be checks that actually make sure that the malicious code is only running in a certain country. That's actually relatively popular for certain classes of malware apps. And in this case, for instance, here the app checks whether it's running in the US, and then depending on this, it does something, or otherwise it does something else. But you might be interested in extracting both, or even all in general, all of these values, right? And if you just do purely dynamic analysis, then you would need to negate all these different path conditions, right? And you would need to make sure that you pass through this branch here in the first place so that this code actually executes at all. So in general, you have this problem of path coverage, right? Which is fairly hard in general, and well, in the most general case, it's even unsolvable, right? So you cannot dynamically cover all the different paths in the program. So this is not really working either, or at least not working very well. And people have tried this before and hit these limits. So the idea behind Harvester was then really to integrate both static and dynamic analysis, and as I will show you on the next few slides, that can really have substantial benefits. So first of all, what we observed was that there are these special kinds of branches in these apps and malware apps in particular that depend not just on any information but on environment information, right? So for instance, this build fingerprint, this is an environment variable that is set by the execution engine, and the SIM country ISO, that's again an environment variable that is set also by the engine or by your phone. There are actually not that many APIs that return these environment values. So there are, well, maybe up to 100 or so, right? So I think it was several dozens that we had back then. And these were relatively easy to list, right? And so we basically had a configuration list in Harvester that told us that these are actually branches, or these are API calls that return environment values. And this then allowed us to very easily determine that these are actually branches that depend on environment values. And now, what this allowed us to do was the following. So first of all, we would actually do a static analysis to figure out, for instance, for number, that this is the program slice here. So this is the set of statements that contributes somehow to the contribution of number. Okay. We would then do the same for message, so that would tell us that this here needs to be included as well. And then first of all, this here, the red code determined this way, this is exactly the code and only the code that is required to actually compute these two values that we are interested in. Okay, and this is then a static slice, so basically a subpart of the program that we would need to execute in order to actually be able to compute these values, right? All the rest, it doesn't actually matter to us, right? I mean, there is this environment check here, this emulator check, but it's not essential to the computation of these values, because if these values are computed at all, then this branch has to be true, right? And so we don't even need to make this part of the slice, because in the end the branch decision isn't really relevant here. We know that this needs to be true, right? Or actually false, it doesn't really matter, right? But we need to take this arrow here, this control flow path, in order to get here. So basically this this emulator check can already be thrown out just by the static analysis. But now we still have this thing here with the second check down here, right? And like I told you before, ideally we would be able to extract both of these values here, but of course, depending on the dynamic execution environment, the sim country ISO can only be set to one of two values, right? So it can be US or it cannot be US, right? But ideally we want it to be both, and so what we then did in Harvester is really that we recognize these special checks that depend on the environment, and if they are part of the slice, then we simply replace them by a check that we can explicitly control. So we basically said, okay, let's make this a dynamic flag, right? So this is basically a dynamic global variable, and then at execution time, so when we then execute the sliced app, we can actually explicitly set this value. So that's just a lot easier to control than, you know, having to install this app on a phone and then, you know, playing around with the operating system to actually, you know, change any of these settings. Maybe, you know, the sim country ISO is even hard to change. You'll probably need to replace your sim. That's really not fun, right? And so with this flag that we can more easily control, we can then make sure at runtime that in one run we would go down this left branch here, and in the other one we would go down the right branch. And that's basically what we do, right? So we then use the static analysis and actually suit, which is the underlying implementation framework of Harvester, to extract this slice out of the app and to replace these special conditionals. And then we basically have some wrapper code that allows us to you know, assign these different executor variables different values. And here it's just a single branch that we need to control. So sometimes there might be 3 or 4 or 5 or so, depending on how long this path actually is. And then obviously we also need to go through all of these Boolean combinations, right? So if we have 5 different variables, we need 2 to the 5 different combinations that we need to test. But actually we found out empirically that, you know, the number of branches that we need to control, it's typically in this order of magnitude. So we haven't seen anything above 5, I think, for realistic Android apps. And that's because typically these paths that we have to these interesting values and these slices that compute these values, they're not actually that large. Yeah, then we also generate a main method, right, that goes through all these different combinations. I guess you get the gist. But this is basically what the app will then execute when it's run in the emulator that actually does the checking. And what's really interesting now is that Harvester can be used also on such heavily obfuscated programs, and it can even benefit from some reiteration of the Harvester approach itself. So let us take a look at what this means. So let's assume we here have a class for name call with some really garbled input like you see here, okay? Then we can configure Harvester to first of all look into these parameters to class for name and try to extract them, right? And so this will basically be a very simple slice that we extract here, and we will execute that slice. And this might lead to the fact that we now have learned that this class for name call actually loads the class SMS manager, okay? And now we can incorporate this actually back into the static analysis. So the static analysis can now learn that the class SMS manager is being loaded here, and it can reiterate its static analysis, and it can also make this part of its slice if it needs to, right? So now we can request other values from the program, and we can reiterate this, so that in the end, for instance, we can then figure out the values of such call to send text message, right? So we could figure out that not just SMS messenger is being loaded here, but in a later method or invoke call, send text message is actually invoked as well. And then in the reiterated step, we could extract the values out of this call here. And the way Harvester implements this is by actually literally embedding these calls. So it's literally replacing on the Jimple representation this class for name call by this one, and the appropriate method invoke call that is seeking to invoke send text message is really replaced using Jimple again by such an invoke statement here. And then in the next iteration, Harvester will pick up on this particular API call, and it will then try to extract these values. And again, we found that typically for the malware we observed, 2 to 3 iterations are sufficient to actually be able to extract all of these instrumentation points and to extract all of their values. Now, like I already said, we did some larger scale evaluation back then. So in particular, we first of all tried to evaluate the Harvester as a tool and how well it works. We first of all found out that it has very high recall and precision. So precision was really 100%. So that means we did not find a single instance where the Harvester approach would tell us about a potential runtime value that was not then actually a real one-time value at runtime. And you can imagine that this is true, right? Because how could it potentially come up with the wrong value, right? So I mean, the code that is executed dynamically is also the same code that is executed by Harvester. The only thing we play around with are these branches, and because we replace the branch conditions, right? And so this is a potential source of imprecision, because when we then go through some branch combinations that are not actually possible at runtime, this could potentially lead to values being computed that can't actually be computed by the actual app. But we didn't observe this, right? So in our experiment, that was actually a non-issue. The recall was 87%, so it was pretty good, but it wasn't perfect. That was just because we still had some technical limitations of the tool. In particular, I remember it was quite challenging to set up these slices so that they would run at all, because as you have already learned, an Android app is not a regular Java program with just a main method. It actually needs to be initialized at the beginning, and we needed to artificially insert such initialization code, and that was not perfect yet at the time. So I'm pretty sure you could actually boost recall if you put more engineering effort into the tool. The efficiency was also great. So in general, we had under 3 minutes of running time, typically even much less. And so this was for a large number of malware samples, right? So over 16,000. And so I think there wasn't a single instance where we had longer running times than this. And we had some really interesting findings. So already in this experiment here, we found some premium rate SMS numbers, some command and control messages. So there are some malware apps that's even very popular these days that communicate with command and control servers. So the malware can be activated and deactivated depending on certain commands that are sent from these servers. And we'll also be able to extract certain URLs, and also, interestingly, an encryption key for WhatsApp data. I'm not sure that is still applicable these days, but back then WhatsApp had its database protected with a single static key that was actually embedded in the app, and we were able to extract that. And a lot of more. That was really interesting, and that actually prompted us to even write a second paper about all of this, because once we had this tool, there was a whole new world opened up to us, which was really interesting to see by running even larger scale experiments. So there's a second paper, Insecurity of Backend as a Service, that we published at Black Hat Europe back then. So here we analyzed in particular Android applications that were using backend as a service services, and I'll still be talking a little bit about what that is and why that is problematic. And using this study, we even made it into the international press. So here's a record from Reuters, and I think we even had an article in the Washington Post back then, because this were really unexpected findings at the time that we uncovered. So let me give you a little bit more context. So there are different cloud service offerings, and by now there are even many more. But back then, what was out there was infrastructure as a service, platform as a service, and software as a service. And there are many different apps, and there are still many more these days that were actually making use of these cloud services. I mean, you can imagine this. You have an Android app these days, and users are entering some data. In some cases, for instance, with the Corona Warn app in Germany, they really looked into data protection, and they wanted to make sure that data is only stored on your phone, and when you erase the app from your phone, all the data is definitely gone. But for most other apps, it's more about actually storing data in the cloud, because the vendors want to make sure that if you migrate, for instance, from one phone to the next, or even if you have multiple phones at the same time, then you can use the same data on all of these devices, right? And this is why basically all of these apps, they all use some cloud storage, right? And this is also called backend as a service. So this became very popular around 2014-15, but it's super popular even these days. And back then there were these services actually offering some of these backend as a services. But yeah, there are even many more these days. The question then, of course, was when apps actually use these services, are they doing this in a secure fashion? And can we probably, using Harvester, figure out when they're not doing it securely? And back then we actually focused on the two most popular services at the time. So back then the service number one was really Parse, and the second most popular one was Amazon Web Services. So Parse is actually owned by Facebook. And yeah, it was really the number one go-to offering back then. Amazon still already had a large market share. I'm not sure if Parse is still number one, but it's probably still pretty popular. Yeah, and so we heavily looked into these apps, and in the next video I will tell you more about what we actually found.